right, great. All right, I believe my screen is visible. If not, do let me know. So today's lecture will be on linked list. Now, what is a linked list and what makes it different? So linked list in a more bookish definition would be a linear data structure consisting of a sequence of elements called nodes, where each node contains a data element and a reference or pointer to the next node in the sequence. Unlike arrays where elements are stored in continuous memory locations, linked lists use dynamic memory allocation to allow elements to be scattered throughout the memory. Each node in a linked list holds a piece of data and reference to the next node in sequence, forming a chain-like structure. So it essentially does something similar to an array. So if you think about an array, what does it look like? Let me annotate on the screen. So say this is an array with 4 indexes, and each of these indexes will contain values. Say this will contain 2, or maybe 22 even works. Okay. And say this will contain 3, this will contain 6, and this will contain 7. Okay, so say this is a array with 4 indexes. Now, usually when we're dealing with arrays, how does it work? An array or an array list. When we try to enter something, usually what we have to do is we have to find out which index we want to enter our value in, and then we have to make space for it. So for example, this goes as 0, 1, 2, 3. Now, if I wanted to add something to this second index, which would be 0, 1, 2, this one, what I would likely have to do is push these two to the side. In other words, increase the length of the array list, and then in that case, 7 would come over here, and 6 would be over here, leaving this block empty for whatever we want to enter. Now, that actually creates complexity and it takes time. So linked list, it gives us an additional advantage where all these data, they're not really in a sequence when it's getting stored. Rather, it's getting stored dynamically in different parts of the memory, but all the data is chained into one sequence where each of the data is within a node, and a node will contain the data and the pointer. So essentially, it could be something like this. We are going to see more examples with proper drawings, but let's just for understanding do this. So say each of these blocks are nodes, right? And so one of the blocks in each node would contain the data. So for example, this right here would be the data, and this right here on the right would be the address. Say C0 T9 or something like that. I wonder. Okay. So now this address would ideally be the address or the location pointing towards the next data. In other words, this right here, this address would be pointing towards this 3 over here. And similarly, it does the same for all of these. So this would point to this, and this would point to this. Now, that's how the general sequence goes. But there are two things. One, this first node over here will be called the head. So we can call this one the head. And for the last node, always the pointer that's pointing to the next location of the nodes will be null. Why? Because that is the last node and it should not point to anything else and it should end over there. So this is pretty much how it looks or works. Let's take a look at different types of linked lists now. So the types of linked list would be singly linked list. In a single linked list, each node points only to the next node in a sequence, and the last node points to null. It's the example that we just saw. Now, a doubly linked list is in this kind of a linked list, each node has pointers on both sides. So one would be pointing to the previous node, the other would be pointing to the next. And in a circular linked list, the last node always points back to the first node. Let's take a look at some images. So for a singly linked list, this would ideally be an example like we've seen earlier. So this is the head, and the location for this is 4800. The head is pointing towards the value 10. And if you see in the pointer part, we have 4900, which is essentially pointing to the next number, which is 15. And if you see the address over here, it's 4900. So similarly, it keeps on going as a chain. The pointer will always hold the address for the next data or the next value. And it will do that till it reaches the very end where it will have nothing else to point to, hence the pointer will be null. Now that's called singly linked list. What does a doubly linked list look like? Something like this, where each of these nodes have contain two pointers, one for the previous node, one for the next node. So the first node, as we know, it does not point to anything that's before it, because it is the first. It has nothing before it, hence the first pointer would be null for the first node. But the pointer pointing to the next node will have the location for the next data or the next node. Similarly, in the next node, since it is being referred from the first node, it will hold the location for node A, whereas it will also point towards the location of node C. This will keep on going in a sequence until it reaches the end, where node D will essentially be pointing towards the previous node, which is C, and also for the next node, it would be null because that's the end of the list. Next, we have circular linked lists. So for circular linked list, it's pretty much the same idea. The only difference is it points back to the first node so that it goes in a full circle. So what we've seen so far in singly linked lists and doubly linked lists is that the last node always points to null. But in this case, the last node will always point to the first node, which you can also call the head. That's about it for the basics. We are going to take a look at some code for it. But for now, do you guys have any questions? All right. Okay, so I guess we can go ahead with the coding part. I'll stop sharing and open up VS Code. Alrighty, okay. So that's good. Let me create a new folder. This is what, March 20. Okay, new folder, linked list.js. Okay, so for this part, we will take a look at a few functions. So to begin with, let's first think about the structure of the list, okay? What each node would ideally look like. Now, for this, we will be looking at classes and constructors in order to create the nodes and the lists. So the first thing we will do is create a class for a node. And inside, I will create a constructor, and that constructor will be taking in parameters like data and next. So next refers to the next node being pointed to. Now, one thing, right now, the list is empty and we don't want it to point to anything. So as default, we can set next as null. And in the constructor, we write this dot data is equal to data, and this dot next is equal to next. All right, okay, so this is the part where we are creating a single node. Let me write some comments. Construct single node. Okay. Now in the next part, what we need to do is create a linked list, a class for the linked list. Now let me call this linked list. All right. And then constructor. So this constructor is not gonna take anything as a parameter because technically it doesn't have to. We're not going to pass anything to this. So this will just create the list itself. So let me write down this. Now, for this constructor, one thing that we have to think about is, so right now the linked list is empty, right? So the first thing that will be entered would ideally be the head of the linked list. So we can call this dot head. I think I missed a dot over there. Okay. This dot head is equal to null because right now it doesn't have anything. Next line, we are going to mention the size of the linked list, which for now is going to be 0 since it's empty. So that makes our constructor. So for the rest, we are going to create a few functions. Let me comment them out first. All right, so let me write insert first node. So we'll do this, and then next could be insert at a given index. So let's do that. Moving forward, what we can do is, okay, so we can create a function for removing at an index. Remove at a given index. Okay. What else? Okay, we could remove duplicates. Remove duplicates. And what else? Okay, so remove last node. Okay, we can do that as well. Let's first do insert first, not actually last node actually. Let's think that's more important. Insert last node. And another function, say we could write down as print. Sorry about that. It's essentially displaying the nodes. Okay, I think that should be good enough. All right, so display linked list. Okay, so let's say these are the functions that we will be working on. Okay. All right. That seems all good. Okay. So the first thing that we would probably want to try out is insert first node. Let's try this. So I'm gonna call this insert first. And for this, I'm gonna take in the data as a parameter. So that's all set. Now, inside this, we have to figure out a way to make sure that we are entering a data and it is in the first node. So we could safely write that this dot head, which means the current node, which is the head because there's no other element in the linked list, will be equals to a new node, and whatever we are getting in as a parameter over here will be passed on to this constructor over here. So data, and then we also should make sure that there's a pointer for this. Okay, so why don't I write down this dot head? So this will be pointing back to the head. Okay. Then another thing that I would probably need to do is increase the size. So this dot size would ideally be plus plus. Okay. So I think, are you talking about the size? Oh, not
No,
sure
for the
which.
when you're inserting the first data,
Okay.
this is the single linked list, right?
Yes, this is a single linked list.
So if it is a single linked list, then this the pointer, this
Mhm.
dot head should be pointing to null.
So how this is working is now this pointer is actually getting a new node that is data and the head itself. So how I'm designing this right now is essentially
Looks like a circular list then.
um, not necessarily. So how this will work is, let me annotate and show, I guess. So say right now, this is the head and I'm inserting into this, right? So if I am inserting, say, 200 over here, this is the first one. But then when I try to use insert first again, what this will do, it will push this head to the right and create a new node over here. And this will be pointing back to the other one. So let's say this could be 100. So whenever I use insert first, this head will just get pushed back and the new node will become the new head. Does that make sense?
Yeah, I understand that. It's just that the pointer of the first node, you're pointing it back to this head.
Yeah, because every time I call this function,
Mm-hmm.
this will be creating a new node over here at the beginning, not in the next location.
Okay.
So yeah, exactly. So this will essentially point to the next one. This won't really point back to whatever is after this.
So when you say this head is equal to new node, and
Mhm.
you're putting the data and the pointer. My issue is in line number 16, where the pointer you're assigning is this dot head. So this dot head, isn't this dot head the one in the beginning that is
Um,
pointing to 100?
so this dot head, okay, so let's kind of break down what's happening. So right now, what we are trying to do is creating a node in the current index, right? All right, so in order to do that, we call the node function. Let me clear this out. We're calling the node class over here. So what this is doing is it's sending in two parameters, data over here as the data, and this dot head as the next pointer, or the data it would be pointing towards next. So essentially what's happening is it seems like I get what you mean by it being circular. So just the annotation button over here. Since the main purpose of this function is to have node entered at the very beginning. Now notice that our next is already null by default. So when we are actually creating this, one second. So it technically does point back to it. So, okay, so this is the new node that we just created. Let's say this was 200 again, right? So this is the new node being created. Now, the thing is, where is it pointing to? If you see, it's pointing back to this dot head. So the idea is it points back to this so that next time we try to I think the annotation would work better like this. Okay. So it sort of points back to this position. That makes sense. In a way, it just points back to this position. So that whenever we call this function again, the next item that's being, or at least the first item right now is pointing towards this over here. If we create a new node, every time you create a new node, it would be created at the very beginning. For the next parts, when we are gonna create, say, insert at a given index, in those parts, the pointers are gonna get changed a little. But just for the insert first part, it keeps on pointing back to the very beginning so that whenever we create a new node, this gets pushed to the right and the new node is being created over here. Does that make sense? I guess when we go farther down the example and see more, it's gonna get a little more clearer. But yeah, if not, I'll go over it again at the end. Okay, so all right, we do have the first node being created. Now, I guess the next thing that we could do is print the list. Now, let's create that function, because then it would be easier to see what's happening. So if we want to print the list, we would need a function called print list. And inside, let's create a variable called current. So I am gonna assign current to this dot head. And for the next part, let's create a loop. So I'm gonna use a while loop just so that the whole thing runs till current becomes null. So this will be current. The next part, this. Okay, so inside the loop, let's do a console.log because I want to see every single element in the list. Console log current dot data. Okay. All right. And once current is being printed, let's change current to the next one. So current dot next. This will point current to the next data. I think this should work. Let's try printing this. All right, so, oh, wait, that's not where it ends. I need to create an instance for the linked list first. So let's do a const, say list is equal to new linked list. Okay, the instance is created. Now let's do list dot insert first. Let's do 200. Okay, and then list dot print list. All right, so node linked list. Let's see what happens. 200. Okay, so it is getting entered. Now, what if I copy this, paste it here, and I change this to 100? Node linked list. All right. So you see, every time I do insert first, what's happening is the first element that got entered, it gets pushed to the right, or it gets sent to a different location, making it the second element in the list and the new one being the first. So it just points back to this one so that every time a new list is created, it knows where to point to the next one. Does that make sense? Is that part clear? I think Samina was having some questions about it. Right, okay. Yeah, it's just so that having this dot head over here makes sure that whenever the new data is being created, it's getting pointed towards the first one. All right, so that was for inserting the first element. Now, what if we want to insert at a given index, right? So if you want to insert at a given index, we can create a function over here. Okay. So let's call this insert at. So this would also get a couple of parameters such as data. And since we are inserting by an index, we would also need to insert pass that index as well. So if we go into how we want to design this, we first need to check if the index is within range. So let's create a if statement to check if the index is greater than 0 and check if the index is greater than the size. For either of these cases, we don't want to do anything to our linked list, so we would just return and send in nothing. Okay, so this will essentially do nothing, but if everything is all right, we could just go ahead and create a new node is equal to new node, and we're going to pass in data. All right, now there are two other variables that you see we did not actually pass in a pointer over here because we will be setting the pointer separately later on. All right, so inside this, we have the data being created, and then we need two variables that would hold the current and previous nodes, right? Okay. So for current, let's set current to this dot head, and let's create another variable for count. And let's set count to 0 actually, because it doesn't have anything right now. Okay. So our current is set to this dot head. Our counter is set to 0. So now one thing that we need to do is create a loop. So I'm going to use a while loop over here to make sure that this loop runs as long as count is less than the index. And inside the loop, what I will do is make sure that I assign the previous index first. Okay, so say I want to enter at 2, 0, 1, and 2. Let me annotate. So 0, 1, and 2. So these are the indexes I want to insert at 2. So there's already a element in 2 right now. So what we would do is change this to previous, as in the element that's already here would become previous, and this would be our new element after this. So, okay, let's try to see it in code. So I will be setting my previous node to current, and I will make sure that my count is getting increased as well. And in the next line, I will make my current to current dot next dot next. So this right here is the node before my index, and this would be the node after my index. Okay, so once that's done, we can do a node dot next is equal to current, and previous dot next will be equal to node. And the last thing I would need to do is set the size. So I'll do size plus plus. This should increase my size as well. All right, great. So now let's actually see it in action. So list dot, I named it insert at, say let's do 400, and I will do 1. Okay, let's see, node and linked list. Right. So you see 400 got entered into the first index. Any questions about this function? All right, perfect. Okay, we still have time. All right, we will do remove. Let's actually try and insert into the last node. So I will call this insert last. Okay, and this also will be getting the data as a parameter. And inside, let's try to see what we can do. So here as well, we would first create the node is equals to new node. And I'm going to pass in the data that I get as a parameter. And I will also need a variable called current that will essentially hold the current index. Now, if we move forward, we have to check if this dot head is null or not. So I'm essentially checking if this is the first index or not. So let me do a exclamation this dot head. Okay, in a case like this, I would just assign this dot head the node that I just created. Otherwise, I will make sure we put it in the very end. So let me set current to this dot head. And now what I will do, I will need a while loop to check if we are going towards the very end of the list. So for while loop, I will put in the condition as current dot next. Now, okay, this is not what I wanted. Current dot next. So this will check if current dot next is null or not, and will keep on running till then. So now inside the while loop, I will essentially just assign the value of current to the last node. So this current dot next, current dot next will make sure that when we reach the very end, as in the next node is null or there's no other node, it will store that particular node.next value in current. Okay, so if we move forward, and then we could just set current dot next is equal to node. So I'm checking if we're at the very end, and if we are at the very end, we are just assigning node to that particular index. And after that, at the very end, I would need to increase the size as well. So let's do that, and I think we are good. So let's try list dot insert last. Let me try 500. Node linked list. Oh, node linked list. Okay, I think I had a spelling error. Okay. 500 gets inserted at the very end. So we are essentially just checking if we are at the very end of the list and then just assigning the value. Any questions? All right, okay, so I assume no, and then we can proceed. So let's first remove, so we have two left, remove at index and remove duplicates. So let's try these out. Let's first try the remove at index part. So it's gonna be kind of similar to insert at index. The idea is very similar. We will call this remove at. This won't be, actually this will be getting a parameter, which will just be the index. This won't get any data though, since we're essentially just removing something. And inside, we are gonna do a check again to make sure that our index is within range. So it should be index greater than 0 and index is not greater than the total length of the list. Okay. And in this case, if it is greater than 0 and it's greater than the actual length of the list, we will be returning nothing. Okay. And on the other hand, what we will do is we will create a, actually, no, I don't need an else statement for this. This, I'm just checking if it is within range. All right, so now what we will do is we are going to create a few variables. So I'm gonna make sure that my current is set to this dot head. And I'm gonna also create a variable to check my previous. Because how this will work is we're gonna remove an index, make sure that the previous index is pointing to the one after, just so that the chain is not broken. So let previous, I'm just creating the variable, and let me create a counter as well. Count equals to 0. Now, if this is the very first index, or the very first element being entered in the list, what would happen is index would ideally be 0. And in those cases, what we do is we assign this dot head to current dot next. I believe I missed an equal to sign, but I can put that in later. Okay. So this dot head would be current dot next. So this dot head would essentially just point to the next one. It won't be showing the first index at all. Now, if that's not the case, if the index isn't 0, what would happen is we would ideally need a while loop to check if my count is less than my index. Doing this, we make sure we traverse through each and every single element till we get to the index itself. Okay, so let me just make sure my count is increasing every time first. Okay, that's done. And in this case, what would happen is my previous would become my current, and my current would become my next node. Current dot next. All right, and doing this will do it for every single index, making sure that when we actually do reach the mentioned index, we have our previous in node stored and our current node stored. That way we could just write down previous.next is equal to current.next. This will skip the current node completely. And doing so, we would also decrease our size as well. So we gotta decrease the size too. So let me try list dot remove at, let's say I want to remove index 1. If I remove index 1, 400 should get removed. Okay, node linked list. Okay, 400 is gone. So it's very similar to the insert part, but the only difference is we're essentially making sure that we have the correct nodes set as previous node and current node. And once all those are set properly, we just make sure to set the pointer from the previous node to skip the one that the current node is in. So essentially it will be current.next. Any questions? Okay, perfect. Then we have one more left, I believe, which is removing duplicates. So let me call this remove duplicates, remove dupes. Okay, so this won't ideally need any parameter because we're not required to send in any index or any data to the function. This could be as it is. And then we create a variable again for the current node. So current is equals to this dot head. Okay. And next we create a function for while current is true, which means current exists, it will keep on running. Let me create another function called maybe the runner, and this will be equal to current. So every time for every single node, runner will hold the current while the entire list is being traversed. Okay, so the reason behind this is we will need another loop that will essentially traverse through the list again to check if there's something exactly the same as that. So while runner dot next is true, as in it's not the end, we will check if runner dot next dot data is equal to my current dot data. If it is, then we write down runner dot next is equal to runner dot next dot next. Doing this, what happens is we skip the duplicate value and just point it to the index or the node after. Now, that is if it is a match, or else what we have to do, we have to make sure if it doesn't match, runner actually takes in the next node. Okay. And once all that is done, we have to do the same for current as well, just so that in case the duplicate isn't found, current does go to the next node and runs the cycle again. So current dot next, it will be current is equal to current dot next. So this should be good. Let me try to enter some duplicates now. Maybe I will duplicate this. All right, okay. So let's try it. List dot remove dupes. All right. Actually, let's comment this out first. Node linked list. Okay, so it does create that. Get rid of the comment. Node linked list. Let's see if it works properly. No, because I entered the name wrong. Okay. All right. Okay, so it does get rid of the extra 500 that was entered over here. Any questions? Any part you want me to go over again? All right. In that case, I have a question for you guys, which is, can you tell me what would be the time complexity for this function, remove dupes? Anyone? What would ideally be the time complexity for this particular function? Right. Any explanation as to why? Why it's going to be n to the power 2? Right. So essentially, for the first while loop, it's going to go through, no, it's going to be on to the power 2. I think I can write it down here. Text. And okay, there it is. On to the power 2. Right, yeah, that's going to be the time complexity, because for this, you can see in the first while loop, what happens is the code goes through all of the nodes, given that, so we're talking about the worst case scenario here, okay? Given that we don't find any duplicates. So the code will go through each and every single node, making the time complexity over here O n. Then again, for the next loop, it would have to go through all those again, making this on as well. Hence, the overall time complexity actually becomes on to the power 2. Yeah, that's about it. Any questions? Anything that you guys want to know about this topic? Because I believe this would be good enough for linked list. There are definitely more examples that you could try with linked list, but these are the very basics, and in most cases, these are the most common things people would likely ask you to code right in front of them. All right, any questions, anyone? Right, perfect. So in that case, we could finish our lecture over here and we could start our lab. So let's take a 10-minute break and we can come back and begin our lab. If you guys have any questions, just raise your hand and we can go to a breakout room and help you out. So yeah, see you guys in 10 minutes.